Welcome dear students. So once again we are with this lecture on separation axioms. In the first lecture of separation axioms we have studied about T-naught spaces and its properties. T-naught space means Kolmogorov space. And then we have studied T1 spaces, that means Frechet spaces. Some of the properties we have done in the previous lectures and some more properties we will do here. But before moving on, once again I like to repeat the definition of a T1 space. A topological space T1 is a space in which if you take any 2 points x and y, then there always exists an open set G that contains x but not y, and there also exists an open set H that contains y but not x. Both these two open sets G and H exist for any two distinct points x and y. If this condition is satisfied, then we say that the space is a T1 space. This we have already covered in the previous lectures, and now I just reminded you about the definitions of a T1 space, and now we'll move on to some properties. Some of the theorems, properties we have already covered in the previous lecture, and now I'll move on to the next properties, next theorems. So first of all, I'm going to prove this example. You can say this is an example. Prove that the set of real numbers with usual topology is a T1 space. So we'll go for the solution. What we want to show actually that are the set of real numbers, and we are having usual topology on it. Usual topology, you know, that is the distance topology, and we want to show that this topological space is a T1 space. So look at diagrammatically what is happening. This is your real line, and if you want to prove that this RU is a T1 space, what you will have to show? You will have to take two distinct points on this line, and then you will have to find two open sets, one containing x and not containing y, the other containing y and not containing x. So first of all, what we have to do? We have to take two distinct points, so x and y. So let x not equal to y be two distinct points of the set R, that means two real numbers. And since we are talking about the real numbers, then there will be some distance between them. So let mod of x minus y be equal to m. This distance I am taking as m. Now what I want to do, consider m by 3. M by 3 means you have trisected this distance m. So this will be m by 3, this will be m by 3, and this will be m by 3. Now consider also, let G be the open interval x minus m by 3, x plus m by 3, and H be the interval y minus m by 3, y plus m by 3. So diagrammatically, simultaneously we will see what is happening. G, this is your x, it is x minus m by 3, this distance is m by 3, so this will also be m by 3 distance on the other side, this distance, and x minus m by 3, x plus m by 3 open interval will be something like this. This is your interval, this interval is your x minus m by 3, x plus m by 3. Similarly, here it is your y, and we are taking, this is your g, and what is your h now? H is y minus m by 3. This is y, this distance is m by 3. So you are starting from here, y minus m by 3, and you will reach something here. This distance will again be m by 3. So this interval, this is your y minus m by 3, y plus m by 3. This interval we are denoting by h. So diagrammatically, this is your g, this is your h. G is an open interval, h is an open interval, and we know that in the set of real numbers, every open interval is an open set. That means G is an open set, H is an open set. That means G and H are both open sets. So I'm writing here, then G and H are open sets such that very clearly your x belongs to G, but y does not belong to G. Similarly, y belongs to H, but x does not belong to H. So I'm writing such that x belongs to G, y does not belong to G, and x does not belong to H, y belongs to H. So what we have done, we have taken two distinct points x and y from the set of real numbers, and we have obtained two open sets G and H such that one of the two elements x is in G but is not in H, and y is in H but is not in G, and that is the condition required to make a topological space T1. So this proves that your R, the set of real numbers with usual topology, that means the distance topology, is a T1 space. So your RU is a T1 space is being proved. Now we will move on to a theorem. Then more and more examples you can take from your book, you can solve, you can verify whether various sets with various topologies are T1 spaces or not. But here I am going to take this theorem now. This is theorem. Let X be a non-empty set with topology tau defined on it, then this topological space X tau is T1 space if and only if singleton set X is closed for every X belonging to the set X. So what we want to prove here, if a space is T1, then if you take any point small x from the set X, the singleton set X will be closed. And since you are having here if and only if, that means the converse is also true. That means if in a topological space every singleton set is closed, then the topological space is T1. So we will have to prove straight as well as backward. That means the converse need also be proved in this case. So how to prove? So I am going to start the proof. So we will have to prove them one by one. In the first part, let X tau be T1 space. This we have assumed. We have assumed that X tau is a T1 space. So what we have to prove now? We have to prove that every singleton set X is closed, whatever the value of small x from the capital X is. So what we will do? We will take an arbitrary point small x from the capital X. Let small x from capital X be an arbitrary point. So we have taken an arbitrary point, and if we show that now the singleton set X is closed, since X is arbitrary, that means every singleton set X is closed. X is an arbitrary point. Choose y belonging to X such that y is not equal to X. That means you can take any point other than X from the set X. Now X is not equal to y. Both X and y are elements of the set X, and the topological space X tau is T1. Therefore, by definition of T1 spaces, there exist open sets G and H such that X belongs to G, Y does not belong to G, and X does not belong to H, Y belongs to H. So that definition we are going to use here. So therefore, there exist open sets, or you can say tau open sets G and H such that X, I am writing here, X belongs to G, Y belongs to H, X does not belong to H, Y does not belong to G. What actually I need? I need one of them, not both. So what I need Y belonging to H. This. I just need this, that Y belongs to H and X does not belong to H. Now Y belongs to H, that means singleton set Y is a subset of H, because Y is an element of H, so the singleton set Y will be the subset of H. And X does not belong to H means H is a subset of complement of the singleton set X. It is very much clear. You can see diagrammatically. Diagrammatically, what is happening? This is your H, and X is not in H, so X is not there. So if you take singleton set X complement, so everything will be there other than X, and H will also be there in the complement of singleton set X. Now what you have done, X was fixed, an arbitrary element X was fixed, and you have chosen Y not equal to X. So you can change Y. X is fixed, but Y can be changed. So take all possible Y's, make this statement, and then take union over all such Y's. So union Y belonging to X, but the condition is that Y is not equal to X. So here also you can say this set H, you can name it as HY. You can name it as HY, and now you can take union over all HY's, but your Y is not equal to X. That is the only condition. HY can be any open set containing Y, but HY is not containing X. So the condition is Y not equal to X. You are taking all singleton sets Y, but when Y is equal to X, we are not taking that particular. So that means what this set is. What this set is. This set is containing every element but not X. And if a set contains every element but not X, then necessarily the set is the complement of the singleton set X. Is it clear, I think? And it is a subset of union of HY's, Y is not equal to X, and is a subset of, on the other side, singleton set X complement. Singleton set X complement is subset of this, and this is a subset of singleton set X complement. So A is a subset of B and B is a subset of A. That means A is equal to B. So from here you can deduce that singleton set X complement is equal to union of all open sets Hy where Y is not equal to X. Now, singleton set X complement is union of open sets. And from our previous knowledge, we know that arbitrary union of open sets is open. And this is arbitrary union of open sets. So this will be an open set. But this is equal to the singleton set X complement, so which proves that singleton set X complement is an open set. And if complement of a set is open, then the set itself will be closed. So this proves that the singleton set X is a closed set, and that is what we required to prove. This is one side. We have proved that if the space is T1, that every singleton set X will be closed. We need to prove the converse also. So I am going to rub it and then we will prove the converse of this theorem. So I am going to prove the converse now. Conversely, suppose that singleton set X is closed for every X belonging to X. And now what we are to prove? We want to prove now that the space is a T1 space. And if we want to prove that the space is T1, what we are to do, what we will have to prove? We will have to prove that for every two distinct elements X and Y, there are open sets G and H such that X belongs to G, Y does not belong to G, and Y belongs to H, X does not belong to H. If we can find two open sets G and H satisfying this condition, for every two distinct points X and Y, the space will become T1 space. So from where we are to start, we will take two arbitrary elements X and Y such that X is not equal to Y. So we will start with, let X not equal to Y be two elements of X. Now we will try to find two open sets G and H, G containing X not containing Y and H containing Y not containing X. That will prove the space is T1. Now note that we are given that singleton set X complement is closed. Singleton set X is closed. This set is closed, that means its complement will be open. So its complement is open. I am going to make a change here. So singleton set X complement is open. I'll name this set as H. So say this is your set H. Now it is very much clear that Y belongs to H and X does not belong to H, because singleton set X complement contains everything other than X. Other than X means X is not there, and everything other than X means Y will be there. So we are able to find an open set H containing Y not containing X. Now take otherwise. X not equal to Y was there. We have used X here. Now use Y. Okay. So singleton set Y complement will also be open on the same lines, because singleton set Y is closed. So its complement will be open. So singleton set Y complement is open. So name it as G. Name it as G. Now this is singleton set Y complement. That means it will contain everything other than Y. That means Y will not be in the set, but every other element will be in the set. That means X will be in the set G, Y will not be in the set G, and G is also an open set. So what we have done, we have taken two distinct elements X and Y from the set X, and we have obtained two open sets G and H, G containing X not containing Y, and H containing Y not containing X, and that is the required condition for the space to be T1. So this implies that your space X tau is a T1 space. So this is the theorem we wanted to prove. Now I'll move on to another theorem. So there are several theorems in separation axioms. We will try to prove each and every theorem. So the next theorem what I am going to take is theorem, and better if you write the statement along with me. Let X be a non-empty set and tau be a topology defined on X, then X tau, the topological space, is T1 if and only if every finite subset of X is closed. So here again we are having if and only if, and this is nothing but the expanded form of the previous theorem. So since we have proved the previous theorem, the proof of this theorem will become now very, very easy. So let us start the proof. For the proof of this theorem, so first I'll take, let the space X tau be T1 space, and now we will show that every finite subset of X is closed. So let us consider a finite subset. Let the set containing elements x1, x2 and so on xn be a finite it is obvious, so let it be a subset of X, and now we will show that this subset is a closed set. Better if you give some name A to this set A. So let A be a finite subset of X. You can write A as, then A can be written as singleton set X1 union singleton set X2 union and so on union singleton set Xn. Space is T1, and in the previous theorem we have proved that the singleton sets will be closed. So that means this set is closed, this set is closed, this set is closed, and from our previous knowledge we know that the finite union of closed sets is closed. So therefore A is closed as singleton sets in T1 space are closed. Just proved, you can say previously proved, and finite union of closed sets is also closed from our previous knowledge. So A is closed, and that was the required to be proved. And now we will move on to the converse part. So converse part, we will suppose that every finite subset of X is closed. Let every finite subset of X is closed. And now what we want to prove? We want to prove that the space X tau is a T1 space. And we are given that every finite subset of X is closed. Note that singleton set X and singleton set Y will also be closed for X not Y belonging to X. If you take any two elements, X and Y, distinct elements from X, then singleton set X will be closed, singleton set Y will be closed, because these are also finite sets. Now these two are closed sets, so this means their complements, X complement H and singleton set Y complement G, are open sets such that X belongs to G, Y does not belong to G, X belongs to H, and you can say and X belongs to H, X does not belong to H, Y belongs to H. So this is nothing, just we have used the concept used in the previous theorem, and this proves that the space is T1. So it was just an expansion of the previous theorem, and now we will move on to the next theorem of T1 spaces, and it says that the property of being a T1 space is a topological property. So here I am going to write the statement theorem: property of being a T1 space is preserved by a 1-1 onto open map. So first of all, try to understand what it wants to say. So before starting the proof, I'll try to make clear the statement of the theorem. Actually, here X tau is given to be a T1 space. X tau is given to be a T1 space. F is a map from X tau to another space, topological space Y rho, such that this map F is 1-1, this is onto, and this is also open map. We are given 1-1 onto open map. So F from a T1 space X tau to another space Y rho is 1-1 onto open map. And what we want to prove? We want to prove that this is also a T1 space. That's what we want to prove. That means, and this property you know very well, that this property is called topological property. If 1-1 onto, or you can say homeomorphic image of a T1 space is T1, then the property of being a T1 space will be known as topological property. So this is what we want to prove. Now we want to prove that this space is T1. So we will have to start from here only. We will take two elements from here, two distinct elements. I will not name it as X and Y. I will name it as you can say M and N, You can take P and Q, you can take R and S, because while taking pre-images, I'll name the pre-images as X and Y. So I'll take two elements P and Q from here. Let P not equal to Q be two elements of Y. I have taken two elements from here, and what I'll try to find two open sets here in row open sets, you can say. I'll try to find two row open sets such that one of them will contain P and not Q, and the other will contain Q and not P, and that will make this topological space Y row a T1 space. So I have taken two distinct elements P and Q from Y row. Since this is onto, so P and Q both will have some pre-image. So what you can say, there exists X not equal to Y, because it is 1 1 also. So if these are distinct, these two will also be distinct. So there will be X not equal to Y in X such that image of X will be P and image of Y will be Q. Now X and Y are also distinct elements. X and Y are distinct elements of X. X and Y are distinct elements of X. But X tau is given to be T1 space. In a T1 space, if you are having two distinct elements, definitely there will be two open sets here, such that one of them will contain X and not Y, the other will contain Y and not X. So there exists, you can say tau open sets now. There exist tau open sets G and H such that X belongs to G, Y does not belong to G, and X does not belongs to H, Y belongs to H. X belongs to G. That means f of X will belong to f of G. We have taken just image on both sides, image of the element and image of the set. Now what is your fx? Your fx is P. So P belongs to f of G. F of G, I'm naming it as G dash. So f of G, this f of G, I have renamed it as G dash. Similarly, f of H, I'll rename it as H dash. Here again, f of Y is not in f of G. F of Y is your Q. So Q does not belong to f of G. F of G is G dash. And on the same lines, f of X does not belong to fh. Now fx once again is P and does not belong to fh. I'll rename it as h dash. Again, f of Y belongs to f of h. F of Y is Q, belongs to f of h is h dash. Now your G and H were both open sets here, and this map F is open. If a map is open, then image of an open set is again open here. So G and H are open, so their images f of G and f of H will be open here, and I have renamed f of G as G dash and f of H as H dash. That means GH are open here. That means G dash and H dash are open here. Open here means they are row open sets. So that means this G dash and this H dash, they are row open sets. So what you have done, you have taken two elements P and Q from Y and you have obtained two row open sets G dash and H dash such that one of them contains P and not Q, the other one contains Q and not P, and that makes the topological space Y row a T1 space. So this means your Y row is a T1 space, and that is what required to be proved. So this was another theorem we have just covered, and we'll move on to another theorem. So this was topological property, and we know that there is one more property that is also important, that is known as hereditary property, which is being preserved from a space to its subspace, and that is the next theorem I'm going to prove here. That theorem, you can say hereditary property. Hereditary property. It says that subspace of a T1 space is also T1 space. The proof is very easy. What we want to prove? We want to prove that if X tau is a T1 space and Y is a subset of X, then the relative subspace, or you can say subspace, denoted as Y, and the topology is denoted as tau Y, that subspace Y tau Y, we will show that that is also a T1 space if X tau is a T1 space. That is what we want to prove. So I'll start the proof now. Let X tau be a T1 space. Let Y be a non-empty subset of X, and Y tau Y be subspace of X tau. One thing I like to remind you how this tau Y is being constructed. Every subset of this tau, whatever the open sets here, they are intersected with Y to obtain the members of tau Y. This is from our previous knowledge, that if a topological space is given and Y is a subset of X, you take each and every member of tau, intersect it with Y, and the resultant will be there in tau Y. So Y tau Y will be constructed in this way, and we have to show that this is also a T1 space. This is given to be a T1 space. Now we want to prove it as T1 space, so what we will have to do, we will have to take two elements from Y, two distinct elements from Y, and we will have to obtain two tau Y open sets G and H, containing both the elements differently, one containing X not containing Y, the other containing Y not containing X. So I'm starting by taking two elements from Y, two distinct elements. So let X not equal to Y be two elements of Y. But Y is a subset of X. So that means X not equal to Y are also members of X. But X tau is a T1 space. So there must be tau open sets G and H, containing one of them and not containing the other. So therefore, there exist tau open sets G and H such that X belongs to G, Y does not belong to G, and X does not belong to H, Y belongs to H. So here this G and H, they are both tau open sets. But I need tau open sets. X and Y are okay because X and Y are elements of Y. So we have two elements from here. But we want the open sets from tau Y. For that, what I will have to do? X belongs to G. X belongs to Y. Now X belongs to G. X also belongs to Y. That means X belongs to G intersection Y. Y does not belong to G. So if you intersect G by any set, Y will not also be there. So Y does not belong to G intersection Y. Similarly, X is not in H. Once X is not in H, it cannot be in a subset of H, and H intersection Y is a subset of H, so X is not in H intersection Y. Y is in H and Y is also in Y, so Y will be in H intersection Y. Once again, I will rename G intersection Y as G dash and H intersection Y as H dash. So X belongs to G dash, Y does not belong to G dash, and X does not belong to H dash, Y belong to H dash. Look once again, G is a tau open set. G is a tau open set, and it is intersected with Y. Tau open set intersected with Y will become tau Y open set. So this G dash will become tau Y open set. Similarly, H dash will also be tau Y open set. So I can say, therefore, there exist tau Y open sets G dash and H dash such that X is in G dash, Y is not there, Y is in H dash, X is not there. So which makes the subspace Y tau Y T1 space. So this means your subspace Y tau Y is a T1 space, and that completes the theorem. So one or two more results I like to do today. So next, what I have proved, let me rub it and then I'll write the statement of the next one. Write the statement first. Theorem. A finite subset of a T1 space has no limit point. Okay, let us start with the proof. First of all, I'll take a T1 space and a finite subset of it. Let X tau be a T1 space, and let A is equal to x1, x2 and so on, xn be a finite subset of X. Now I will show that A has no limit point. One thing you must know, that A is a finite set, and in a T1 space finite sets are closed. So this is a closed set, and a closed set contains all its limit points. I'm writing it now. A is closed. Why? Because A is finite subset of T1 space, and finite subset of T1 space are closed, so A is closed. And every closed set contains all its limit points. So this means A has no limit point outside A. So this means A has no limit point outside A. So whatever the limit point of A will be within the set A. And since we have to prove that A has no limit point, now finally we will prove that no point here is a limit point of A. A is not having any limit point outside this, and we will prove that A has no limit point inside also. That means A will have no limit point. So we will take any arbitrary element from here. Let xi be any element of A. Any element of A. We will show that xi is not a limit point of A. That means no point of A is a limit point of A, and no point outside A is a limit point of A. That means A has no limit point. Now xi is an element of A. Now consider this set. x1, x2, move up to xi minus 1, leave xi, I plus 1, and once again to xn. That means what we have done, we have excluded the element xi from here. So this set G I am taking. This set G. I am writing this set. Now, intersection of this set with the singleton set xi is phi. So this set, this open set does not contain the point xi. That means xi is not a limit point of A, because its intersection with this set is phi. So that means xi has no limit point, A has no limit point inside A. A is having no limit point inside A, and A is having no limit point outside A. So it means A is having no limit point. So this means A has no limit point. So this was the theorem, and here I am going to stop this video. So try to understand these things. If you face any problem, you can ask your problem through WhatsApp number. My WhatsApp number is there. I am writing once again. My WhatsApp number is 9041404543. You can ask your problem here. You can ask your problem in comment box, and your query, your question will be answered maybe in the next video or in the next to next video. So till then, wait for the next video, complete it, and report me if you have completed, if you have understood these theorems. Thank you once again.